Hello everybody, my name is Jerry Salan and I am the CEO and owner of Nailus Engineering Services. Today's webinar is titled Energetic Material Process Development Using the EasyMax System. First I'm going to give you a little bit of background about our company, then a little bit of background about the project, and then we're going to dive right into some of the technical information. And I really hope you enjoy this. Nailus Engineering really enjoys working with its customers to develop chemical processes that are transitionable to the plant environment. We do this by first evaluating the chemistry in the laboratory using a variety of in situ and offline tools. Hopefully we can identify any engineering challenges that may be problematic as we start to scale up. We develop kinetic, mixing, and process models using various software tools. And then finally we like to design, build, and test the equipment. Hopefully the output of all of this work is a low-cost chemical process. Energetic materials are really just special chemicals. When I say special, they just react differently to stimuli such as impact, friction, electrostatic discharge, or even thermal stability. These materials are generally used in formulations for explosives, propellants, pyrotechnics, or reactive materials, but the process development is very similar to that you would see in the fine chemical or pharmaceutical industries.
You may wonder why the Department of Defense is investing a lot of money in novel energetic materials. The reason is quite simple. The Department of Defense is looking for insensitive munitions that will go off when they are supposed to go off and not go off when they're not supposed to go off. This is a picture on the deck of the USS Forrestal where there was a fire aboard the ship, and the fire resulted in munitions being exposed to high temperatures. These materials detonated and caused loss of life, loss of equipment. It was a very trying time for the Navy, and they launched the insensitive munitions program. So these insensitive molecules that we're going to be talking about today are to address these needs.
So one of those molecules is DAF. The starting material is the diaminofurasan, and it's a oxidation process. And as we step right through the oxidation, we see that we form the hydroxylamine and the nitrosofurasan. And when those two come together, they form the desired product, which is DAF, the diaminoazoxyfurasan. If the oxidation goes a little too far, you may form an impurity named aminonitrofurasan, or ANF. And if the conditions aren't exactly correct, we may form the diaminoazofurasan, or DAZEF. We're going to talk about how pH influences the formation of the two impurities in the desired product. From this, we're going to develop a kinetic model and hopefully design a system that will produce large quantities of DAF and minimize the DAZEF and ANF. That was the objective of this project. Another way of looking at this is these are the equations that we're going to be inputting into our DynoChem kinetic model. So equations 1 and 2 show the formation of the intermediates, and we'd like to know what their reaction rate constants are. Equation 3 shows the formation of the first impurity, ANF. Equation 4 shows the product, DAF. And finally, equation 5, the second impurity, DAZEF. Using these equations, we will build into a kinetic model and aid in our design of a continuous process. With everything, there's always process constraints. In this particular project, we wanted to make a large quantity of material in a short period of time. So when we looked at the batch oxone process, it involved charging water to the reactor, the diaminofurasan to the reactor, sodium bicarb to the reactor, and then finally the oxidizer. They then waited a period of time until gas generation subsided. We did a second charge of sodium bicarb and a second charge of the oxone to the reactor. Waited another period of time, then we filtered off the solids. What we noticed is, as we started to scale this up, is that there's 60 volumes of water that are required for the reaction to take place. That's a large amount of water for a batch process. We thought that by going to a continuous process, we could actually speed things up in terms of process development by not having to go to the larger scales and get good quality material. One of the challenges that we faced with developing a continuous process was looking at the influence of pH on purity and yield. We knew what the batch process yielded, but the batch process also had varying pH throughout the duration of the dose of the oxone. So we wanted to go back and look at that batch process and see how the influence of pH was going to influence our impurity profile and also yield. Fortunate for us, the DAF molecule is not new. The DAF molecule has been around for decades, and there's plenty of literature out there that has done some studies on the influence of pH on the product DAF and DAZEF and ANF impurities. So what we wanted to do was go back and look at that literature and sort of bracket what pH range we wanted to study. The other thing we wanted to do was evaluate the batch process using the oxone and see what type of range, pH range, they were operating in. We did that utilizing the reaction calorimeter. So the first time we ran this reaction was in the Mettler-Toledo RC1, and we captured heat flow data and also traced what the pH range would be during the batch process. What this allowed us to do was bracket the pH range that we wanted to be in when we started doing process development work, because we knew that the batch process gave good quality material and a decent yield, so we didn't want to deviate too much from the batch process that they already had. We simply wanted to convert it over to the continuous process. So from this, even though I can't show you the exact pH range right now, that's proprietary, and we can determine what range they were operating in, and that would be used in our EasyMax process development. So here's our system. The reaction monitoring system we chose is the EasyMax system. And those of you who have done process development over the years, it's very difficult to find good tools that are out there that can give you good temperature control, good pH control, easy to sample. This particular system, the EasyMax, you can have a low reaction volume. We were operating in the range between 15 and 20 mils per experiment. It was efficient, and one of the very nice things was that there's no chiller required. This actually utilizes Peltier cooling, and not having a big bulky chiller in your lab is a big benefit. Here's a nice picture of our setup that we use for the DAF process development using the EasyMax system. We used a universal control box, and the universal control box did two things. It brought back our pH signal, but it also controlled the Ismatec peristaltic pump that we utilized for dosing in the sodium carbonate solution as a function of pH. And the iControl software, all we simply did is input what pH value we wanted to control at, and the system did everything for us. And what we got was a lot of data at varying pH and isolated solids that we were able to evaluate and see the influence of pH on those isolated solids. So our pH screen was run in the EasyMax system. We would run the reactions at the same temperature and vary pH. We isolated the solids. We got a variety of data from this. We obtained yield. We also looked at thermal stability. We also identified the optimal pH that we wanted to use for the continuous process. Finally, we did find one surprise, which was the formation of a new impurity, not something that is desirable at any stage of process development, but we did find that this impurity was what was influencing the thermal stability of the DAF isolated solids. So it was a good thing to find this early on during your screen. And we'll talk a little bit about that data here in the next couple of slides. First thing that you need for any process development effort is a good method to track your starting material, intermediates, products, and impurities. This particular process, we developed an HPLC method. We were able to track the DAF, the ANF, the DAF, and the DAS-EF. And also, as we pointed out in the previous slide, we tracked that impurity C. This is the material that was wreaking havoc on our thermal stability, and we didn't know until this screen which impurity was actually causing the problem. But when you're able to quantify how much of a substance is in the material and also evaluate the DSC data in parallel, you can start to see that the influence or increase in concentration of impurity C dramatically influenced the DSC onset. This slide is a summary of our HPLC area percent data on the isolated solids of reactions that were run at varying pHs. And what we can see is that mainly impurity C is influenced by the change in pH. We also see that the isolated yield is dramatically influenced by the change of pH and also DSC onset. And there's a balance here. The isolated yield is mainly reduced as a function of pH because you have poorer conversion of the diaminofurazan to the product DAAF. And that is in the form of DAF either doesn't convert or it converts to ANF. And what you don't see here is the amount of ANF that's in the liquors dramatically increases with increase in pH. So the balance that we were going to fight is getting good DSC onset, decent yield, and minimizing that impurity C, which is directly influencing the DSC onset. So the next slide I'm going to show you is an overlay of the DSC data from varying batches at different pHs and seeing that the influence of thermal stability is dramatically influenced by this impurity C. So here's the DSC overlay, and as you can see, we We start off at a quite low pH in blue, and we start to increase pH value with the purple, then the black, then the lighter purple, and then the green. And then the control is our red, which is the batch process. One thing to point out is that some of these DSC overlays have a nice clean melt at around 254 degrees C, and that is desirable for the cook-off test that we're eventually going to. And this tells you whether or not this material, or it gives an indication of whether or not this material is going to perform well in a cook-off test when you put it into a fire. And the melt was desirable, and you can see that as you start to decrease the pH, that melt starts to disappear. And especially with pH at the 2 stars, you can see that the onset is around 232 or so, and 228. But there's no melt at all that occurs with that pH value. So that was important to us, is making sure that we had a nice clean melt. So we took that into account when selecting pH. Now that we've completed our reaction screen and evaluated the pH values that will lead to thermally stable, high-yielding product, we now turn our attention to the reactor design. With this, we want to look at 2 different models. One's going to be a mixing model where we use EasyMax software, and the second's going to be a kinetic model where we use the DynoChem software. So we're going to walk you through several slides that talk about how we developed these 2 models, and then finally we're going to talk about how we tested our support equipment, including the pumps and pH control feedback loop. Mixing is probably one of the most overlooked challenges when scaling a process up. In this particular case, we're using pH control feedback loops. And mixing can be critical to getting a good pH value, which is now your process variable for controlling pH. So if your detection of pH is not adequate, you're going to have poor control over the system, overall system. That can lead to mixing gradients, resulting in impurities, which we've already identified in previous slides. Also, the location of the pH probe can also be critical. If we have the pH probe located right next to, say, for example, the dip tube where the sodium carbonate is going to be bleeding in, you may have some challenges with lags and readout of what the pH actually is versus the pump feeding in the sodium carbonate, which could result in a disaster. The final bullet we have here is solids dispersion. Poor mixing also can result in some solids being in the reactor train much longer than the other solids. For example, if the solids aren't dispersed evenly in the vertical direction of the chemical reactor, you may have the heavier solids start to fall down. They can grow, they can get bigger in particle size and actually start to agglomerate. We don't want to see this happen, so we did model what the solids dispersion would look like for the particular particle sizes that we've seen in the laboratory. Scale-down experiments are an excellent and cheap way of finding out what's going to happen in terms of mixing sensitivities when you go to the plant. If you can identify the equipment that you're going to go to in the plant environment, you can model it in EasyMax, you can determine what the mixing parameters are, and then mimic those in the laboratory. By doing this, you can find out whether or not you're going to have a mixing sensitivity as you start to scale up. If you do have a mixing sensitivity, this is your opportunity to change the plant equipment and maybe improve the mixing capability of the system so that you don't see the mixing sensitivity as you scale up. So that last bullet I want to point out is that if you're generating data in the lab that's not matching the mixing parameters that you're going to in the plant, you may be just setting yourself up for a disaster. And it's a good idea to stop before you start doing your development work, figure out what equipment you're going to in the plant, and mimic what that degree of mixing is in the laboratory environment. There are many things that we were able to model using the EasyMax software for this particular process, but I want to share with you just a couple of the things that we did. One of the exercises we went through was a tracer exercise where we were injecting the sodium carbonate feed at different locations, the oxone feed at different locations, trying to determine if we're going to use dip tubes or if we're going to do above surface additions. And using this tracer exercise allowed us to make a good decision on where the sodium carbonate feed would eventually be, where the oxone feed would eventually be. And on the next slide, I'm going to show you an example of comparing even upward versus downward pumping impellers when you're using a pH feedback control loop, because the pH gradients could change dramatically just by changing your configuration from an upward to a downward pumping system. And the second thing is location. Something that's also overlooked is sensor location. Sometimes reactors have fixed sensors, and you're not really sure if you're going to get good feedback from that sensor. You might have you might be in an area of poor mixing, and you might get a lot of noise from the sensor
in terms of gradients. So your pH may look like it's varying between 5 and 7 over a period of time, when in actuality that's actually where the sodium carbonate feed is bleeding in, right by where the sensor is located. So by changing their sensor location, or even changing some of the equipment components, you can get a better mixing in that sensor location. In our situation, we were designing the sensor to be input into the reactor, so the EasyMax exercise allowed us to determine where a good location would be for the sensor in comparison, and a relative comparison to where the feed of the oxone and the sodium carbonate would be. So here's the graph that we were just talking about. Is that we have two tracer concentrations, and we're looking at that sensor location that I'd shown you on the previous slide. And this is just a comparison of the upward versus the downward pumping impeller with that sensor location and the equipment configuration that we were using. Now, this only has a single impeller on the shaft. We eventually went to a dual impeller on the shaft, and you could do the same exercise for that configuration. But as you can see, is when we start to dose in whatever it might be, the oxone or the sodium carbonate feed, in the first example, which is the upward pumping impeller, we see a nice steady increase until you hit approximately 1, which is perfect mixing in this case. And the second one, the second figure that you see there with the downward pumping impeller, we see strong deviations, above 2, between 2 and 2.5. And that could happen each time your pump kicks on for the PID loop. So if you want to see pH going a bit haywire, this is the configuration to pick for this equipment configuration, this sensor location, and the dose being where the dose is located. So the model allows you to play around to try and figure out where you want to have your sensors, where you want to have your feed locations, and it doesn't cost you anything except for the price of the software. But you can play around with your equipment before you actually build it and find out the hard way. Okay, this is really where the fun begins. Is we're now looking at the kinetic model, and I took a clip here right out of Fogler. This is Elements of Chemical Reaction Engineering. And what we're going to do is get the data required to determine the rate laws for this particular reaction, the DAF reaction, and we're going to size a continuous stirred tank reactor train. And the next few slides, we're going to walk through how we acquired the data to feed into the kinetic model. We use the DynoChem software we talked about earlier. We're going to demonstrate how to develop the Liebenspiel plots. And finally, we're going to show you how we got the volume of the continuous stirred tank reactors that we utilized in the plant. So the first order of business when developing the kinetic model is determining what are you going to monitor. And with this particular process, we could monitor several things. We had a great HPLC method that we could monitor the diaminofurazan, the starting material. We could see our impurities, and we could see our product. So with this, we had our 5 equations we're going to solve. We're now going to go forward and get the data required to get these rate constants. Whenever doing process development, you're always going to run into a new challenge, and that was the case with this particular process as well. When we were running these reactions, they're very dilute. Remember, there's 60 volumes in water. They're also heterogeneous, so as a function of time, we have the solids, which is the product and one of the impurities that are precipitating out over time. So when you're typically running batch experiments and you're collecting kinetic data, it's nice when you have everything nice and homogeneous. You can pull samples over a period of time. You can get concentrations over a period of time. Not so with this particular process because of the heterogeneous nature of the reaction mixture. So what we did instead is we fed the reagent in as fast as possible while maintaining pH. Another challenge was maintaining pH. As we did that, we then selected specific time points where we quenched the entire reaction mixture. So the entire reaction mixture contents was poured into DMSO, where we quenched the reaction. We then diluted that up, and we shot that onto the HPLC for analysis. So basically, we took the entire reaction mixture, diluted it up for an HPLC sample, and we could monitor the concentration of starting material, impurity, and products. We did this at several different time points, and you can see that the DynoChem did a great job fitting. You will see that the diaminofurazan, which is the blue squares, we do have a lag, and we think what's going on is the time for sampling took a little bit longer than we wanted to, because you have to take the lid off, get the sample into the DMSO, and that's why the model is actually predicting properly, and our time points are probably incorrect for the HPLC. And it's just because there was a time lag there with those initial samples when the kinetics are very, very strong and fast. Okay, the next slide, we're going to show you some of the data that we got from the HPLC monitoring. So here's that beautiful data. We now have, as a function of time, we can monitor the diaminofurazan, the starting material, the aminonitrofurazan, one of the impurities, DAF, which is our product, and the DAZIF, which is another one of the impurities. We track all this as a function of time. We can have Dynachem do the fitting, and we can get our rate law. So after Dynachem has done its fitting, we now have our rate constants. The rate equation has been determined, and now it's time to move on to the Levenspiel plots, where we're actually going to look at sizing the reactors through a graphical representation of sizing the reactors using that design equation that we talked about earlier for volume of a CSTR. I really like the Levenspiel plot because it's a good graphical representation of your volume of your CSTR design equation. And in this case, we've got the rate equation from Dynachem, and it's plotted here. Now we're going to start making decisions about the feed rate of the material coming into the first CSTR, how many CSTRs we plan on having in series, what the conversion at the output of each of those CSTRs will be. And this is all going to be driven by economics and the available equipment that you have in the plant. The purchase of capital equipment is definitely not on the top of anybody's list to do, so we're going to try and make use of equipment that's already there. And by using these Levenspiel plots, it's nice because you can just say, okay, I have a 50-liter reactor. The area under this curve's got to be 50, and that's when we're going to start drawing boxes, and we'll show you a couple of examples of how to do a quick design using these Levenspiel plots. Here I've designated a specific FA0 input into the system, which again changes the values of our y-axis. And now we're going to start looking at using two 50-liter continuous stirred tank reactors, and it'll tell us what the output in terms of conversion will be from the system. So here we find with two CSTRs in series at fixed volumes of 50 liters, we're basically just drawing boxes, and the area under the curve represents the volume of the CSTR. Here we're going to get to approximately 86% conversion in the first CSTR, and we're going to get to approximately 97% conversion in the second CSTR. Now, if you change the input or the flow rates into the system, you can easily start to increase your conversion. If you change the volume of the reactor, again, you can start to increase your conversion. So there's a lot of levers that you can see from this one graph that can be utilized to change either conversion or reactor volume size just by one graph. All this was done using the Dynachem software and then an Excel spreadsheet to draw the Levenspiel plots. With all this information in hand, we can now sit down with our customer and look at the design of the 50-liter CSTR system. As you can see, we have several scales that we're going to be using to meter material off of into the reactors. The first reactor is going to receive the DAF solution, the oxone solution, and the sodium carbonate solution. We found that there was definitely a need to have a fourth pump that would be metering in sodium carbonate and monitoring and controlling pH in that second reactor, because the pH does drop significantly into that second reactor, which can cause impurity formation there as well. And then we have a pump that will pump reagent, the slurry from the first reactor to the second reactor, and finally from the second reactor onto the Buchner filter where we isolate our solids. So here's our design, and this is what we're going to run. But before we were able to go to the 50-liter CSTR, we had to take a step backwards and do the proof of concept, a scale-down experiment in the laboratory. Whenever we're scaling up explosives, we're always very happy to complete a proof of concept at the much smaller scale in the laboratory before going to the larger scale. This not only verifies your mixing model and your kinetic model, but also gives you more sense of security when you go to scale this process up into the larger scale. You get familiar with the scales, you get familiar with your feed streams and the pumps and how the system is going to respond. With this, we produce some high quality product and we're able to ship it off to our customer for evaluation, and it looked very good. So we went to the next step, which was the 50-liter process. But before going to the 50-liter process, we wanted to use Dynachem a little bit more. We knew that scaling this up and taking it to the larger scale, there was going to be a requirement of time. And when you have a 24-hour operation, and especially with explosives, you need two people each shift for a 12-hour shift. So we wanted to look at what was going to be more costly, getting that last bit of conversion of the diaminofluorescein out, or the days of operation. What's going to be more costly? So there's always going to be this balance between your raw material costs and your labor costs. And with this, we were able to decide how long we wanted to operate versus how much DAF conversion would be. We used the Dynachem model to help make that decision for us. Once the decision was made, we nailed down what the flow rates of the oxone and DAF would be, and we moved on to the next step, which was actually running the process in the plant. Here's a little snapshot of what the process actually looked like. Just two 50-liter CSTRs in series, several pumps that were metering reagents into the reactors, and the output was product on the filter, which was what was our goal, and we were very happy to see it on there. So in summary, we were able to develop a mixing model which avoided the mixing challenges at the proposed scale, which was a 50-liter system. We developed a kinetic model utilizing pH control and quenched several reactions at different time points. The EasyMax system was key in getting us the data that we needed to put into this dynochem model. We developed that continuous process to produce large quantities of material safely, and now our new focus is on reducing the cost of that starting material, the diaminofurazane. There's a lot of people that contributed to this effort. I want to thank a few of them, and I know there's more that are out there that may be off this list. But thank you all very much for your attention today, and if there's any questions, please give a call in, and we'll be happy to answer it.